Hey, pre-calculus friends, we are in chapter 1 still. We're looking at section 1.7. We're going to talk about piecewise functions. So we are still talking about linear functions or functions with kind of lines in them, but today we're going to take, I guess, a little step away from them and talk about functions that are related to the linear function. So the first is the idea of a piecewise function. Sometimes I like to call it a Frankenstein function, and they will look something like this. So basically, you'll have your regular XY axis, and if you were to graph a piecewise function, you notice that part of the graph might be this line, and then another part of the graph would be this line, and then you might get something like this. And I'm doing it in different colors so you can recognize that sometimes piecewise function, Frankenstein function, is taking three different things, or three, four, or five, however many you need, to create a relationship that you want to determine. So a piecewise function is a function that has a lot of different pieces, and sometimes it'll be written in such a way like this. So your equation will look like this. It'll be f of x. This whole thing would be considered f of x. This is the function of x. And it's given, you've got three different parts depending on what part of oh golly, what part of the domain we're dealing with. Sorry guys, I'm here. So anyway, so the part of the domain that we're dealing with in this portion is x less than or equal to 0, and so this graph is there for all x values less than or equal to 0. So you might even probably should have had a little arrow here, so that continues on forever and ever. And since it stays all the way up here until x is equal to 0, good. And then this graph over here that I have in purple is just a y equals 3 graph, horizontal line all the way from x is greater than 0 over to x is equal to 6. So we can assume that, well, let me highlight this first. So that is the purple portion, and we can assume that this right here would be 6 on the x-axis, this being 0, we know. And so that gives us another part of the domain that is referenced by this graph. And then the final part that we're going to talk about is this part in yellow, or orange rather, and this part is through this graph is going to have maybe an increased slope. It's going to have its y-intercept would be all the way down here at -6, but we don't see that because we only want the part of the graph that is where such that x is greater than 6. So this is what a piecewise function looks like. I hope that made sense. And so we're going to be studying those and graphing those. And then another type of function that we're going to work with are called step functions. So in general, a step function is going to be a function whose graphs are kind of like a piecewise function, except there's like steps the whole way through the graph, okay? So literally that's going to be a step function. And the step function that we use the most is, that we'll talk about, is the greatest integer function. So I'm trying to underline. So if we were to consider the greatest integer function, let's think about what it means. The greatest integer function is a function that takes any number, and it associates it with the integer that is the integer that is less than or equal to that number that is the greatest. I know it sounds crazy. Let me explain. I'm going to call it the I'm going to call it the age function in a way. You know how if you have a little sibling, or if when you were little, if you were like 1.5, like if you were 1.5, maybe not then, let's say you were 11.5, you'd be like, I'm 11.5, and somebody would be like, yeah, fine, you're 11, right? So if you had to write that information down on, let's say, a piece of paper, and they were like, what's the age of your child? It would be like, you're 11. Right now you might be 17.6, but if for all intents and purposes you are 17, you have not reached 18. So what the greatest integer function does is it rounds any integer, or any real number. It rounds real number to an integer value that is less than or equal to, it is the greatest integer that is less than or equal to the number. So I like to think about it in terms of ages. So I'm going to graph that and think about that together. Let's do that together, I mean. Okay, so let's pretend we're dealing with somebody who is, or let's think we're thinking about somebody who's just born. Clearly they're 0. So when we're at 0, we are 0, right? That makes perfect sense. And so the x value would be 0, then the y value is 0. Well, remember, this is the greatest integer function, and oftentimes I should show how it's written. Y is equal to, and you'll see like a double bracket thing. So this is what the greatest integer function notation looks like, or you'll see f of x. I'm going to put that right here. And remember, the greatest integer function is just a type of step function. So anyway, if we put in 0, we get 0 out. We put in 0.5. Remember, we're not rounding up, we're rounding down to the nearest integer. So we put 0 here. So at 1.5 on x, we're still on the x-axis. We're still at 0 for the y value. And if I were to go to 0.957 here, we'd still be at 0 because we're rounding down to, or we're rounding to the nearest integer that is less than or equal to, right? So it's the greatest one that's less than or equal to the value. And all of that's going to be cool until I get to the number 1. When I get to the number 1, the answer is going to be 1. The value for y has to be 1. So I put an open circle here and I put a dot here to say, okay, yes, this is going to be 1. And so everything in between that, even 1.2, will now be rounded or sent to 1. So notice what the range is. The range is going to be all these integers, right? So if I was at 1.975, I'd still have to round to 1. Remember, like the analogy that I use, if your little brother or sister says, oh, I'm 1.9 blah blah blah, and they can be truthful about that. If I'm filling out paperwork for them and it says, how old is your child, I have to say 1. Does that make sense? So at 1, we're at 1. At 1.5, we're at 1. And so you see slowly, if I get past, as soon as I get to 2, I'm at 2 for the y value. Let's put some numbers here. And then everything in between 2 up to 3 is going to be mapped to 2, and I get these steps. Are you guys with me? If not, let's talk about it, because this is some cool stuff. All right, so this is how we get the steps, and they orient exactly the same way in the negative direction, even though it's a little bit harder to think about ages when we talk about negative direction. But if you think about a number like, let's say this would be negative 0.05, what is the greatest integer that is less than or equal to 0.5? That would be negative 1. That's why here at negative 0.5, we're down here at negative 1. Are you guys kind of with me? I'm hoping that makes sense. Let's look at the absolute value function. And so this function is going to look like y equals the absolute value of x. This will be like the parent function for that. So y equals the absolute value of x, or f of x is equal to the absolute value of x. And basically what's going to happen here is when you have this kind of a graph, like y equals x, let's take that graph, let's take that function for a minute. It would just be this beautiful diagonal line, because if x is, if x is 4, y would have to also be 4, and you get the same tit for tat value that whole time. But when I put an absolute value around it, what I've now said is that y can never be negative. In fact, y will always be the positive counterpart of the whatever value it is. So down here where x is, let's say, negative 3 and y is negative 3, I'm not going to have a negative 3 when I'm dealing with that y portion. I'm going to actually have a positive 3. So my graph for an absolute value function, you've probably seen this before, but my graph for an absolute value function is going to be a V, because this portion down here will be obliterated by the absolute value bar. So you're going to get a V value. Anytime you're dealing with absolute value, you'll have a V formation for your graph. Let's look at some examples. So here's an opportunity for us in example 1 to graph a piecewise function. I really do like to use colors and try to help myself think about what this piecewise function means. So let's focus on this orange portion really quickly. First of all, let's observe the domain. The domain is from all x values that are less than or equal to negative 2. And so that lets me know that if I come over here at negative 2 on my x-axis, my graph will, in a sense, start here and then go all the way back. So the realm, if you will, of this graph will be on this part of the coordinate plane, only from negative 2 back. And so now it says the function f of x is equal to 1 if x is, in this situation, less than or equal to negative 2. So I'm going to graph y equals 1 in this realm. Is that making sense, guys? So here's 1 on my y-axis, and then y equals 1. I'm going to put a dot here because that is true when x is less than or equal to -2. So I'm going to do that. Let's put a 1 here. I'm trying to make this look neat, guys. Be with me here. As soon as I say it, it's like it goes haywire. Anyway, so we're going to have this graph like this. All right. So now we need to check the next realm by considering what the domain is. And so this domain here for this portion of the graph goes from -2, not including -2, but it starts at -2 and it goes all the way up to +3. And that realm is here, this blue realm. And so what I'm going to do is I'm going to calculate the value since it's a line, 2 plus x, that's a line, that's a linear equation, y equals 2 plus x. I'm going to calculate the beginning and the end point and then just connect the dots. So remember the beginning of this realm is at -2, but not including -2, though my graph doesn't really say that. Here's how I represent that in terms of the situation going on here. So watch this. I'm going to calculate the two values that I said just for this portion. So at -2, even though we can't really do that, my value would be 0. And then at 3, which is the very end of this, my value would be 5. And so I'm using these 2 points to gather the line. So if at -2 my value is 0, and I can't really graph the -2 because that's not the 0 because that's not a part of this graph, I put an open circle there to represent that point. And then everything else is solidified. So I'm going to go to 3, 5. Let's say 1, 2, 3, 4, and 5 is here. So then my line gets all the way up to here. This is 0.35, which is included in the graph. And so there's my piecewise function. It looks like that. So this piecewise function is not continuous. There's like a skip here, and that's totally okay. Notice there's not two values for x equals -2. There's only one value. X equals -2 is defined here by 1. X equals -2 is not defined in the blue region. And so we know that the next value that's defined is going to be whatever comes after, just after -2. You guys with me? All right, let's do this final portion. So this last portion that we'll highlight in gray will refer to this whole section. That's everything that comes after 3, but not including 3. So the graph will start at, well, I'm going to put a 3 in there, even though I know it doesn't equal 3. I'm going to put a 3 in there. When x is equal to 3, we get 2x, which is 2 times 3, which is 6. So this value would be up here at 6, but remember, I can't actually put it in there. I put an open circle. And then I figure out any other point that's going to give me the rest, because this is a linear equation, y equals 2x. So if I plug in, let's say 4, I should be up at 8. I know I'm all in the graph. This is 6, 7, 8. Let's say it's right here. And then so the last portion of my graph should be like this. And all of this is the gray region, if you guys didn't get that. All right, hopefully this makes a little bit of sense. Let's look at another example. So example 2 is just asking us to graph f of x is equal to, and remember this kind of double bracket vibe would be the greatest integer function. And so we're just going to do what we did last time. Mentally, we're going to think about where to put these x values. So when the x value is 0, y is 0. When the x value is 0.5, y is still 0. As soon as we get to 1, in a sense, our graph pops up to 1. And then we continue, if x is 1.5, y is still 1, until we get to 2. So we're going to get this graph at this point, and we've seen it before. It looks kind of like lollipops laying on its side, and then you will get a similar graph in this direction as well. It's not too bad. So in the beginning of the chapter, we were introduced to the concept of tax brackets. And so what we have here in example 3 is kind of looking back at that information. So here we have tax brackets given different income values, right? So from 0 from this, we get 15%, so forth and so on. This is probably old information. I'm not sure if it's still accurate, but whatever. We can still use it for our problem. And so basically what we're doing is we are considering what exactly this is going to look like in terms of a graph. And I'm hoping you guys can feel that this is really just like a domain and a certain value at that domain and the domain and the domain. And so what we have is really a piecewise function. So I'm probably going to have to show it in another video. So I'm going to show it in the next video where we're going to graph this information, and then we'll find out what is the tax bracket of a person who makes $70,000. So I'll see you guys soon.